Good morning all. So today let us discuss the determination of CD for Orificemeter. An Orificemeter is a simple device made up of a metallic plate with a center hole and fitted inside a pipeline. It is used as a flow measurement device in a closed conduits. The discharge computation is based on a Bernoulli's principle which is applied at the inlet of the Orificemeter and at a Vena contract of stream. The working principle is similar to Venturimeter. Usually the value of CD is less than that of the Venturimeter, that is mainly due to the more losses and as sudden contraction is involved. So you can observe the Venturimeter, Orificemeter setup. So this is the points. So this is the differential manometer. This is the direction of flow. So here you can notice the orifice plate. So the main aim of the experiment is to determine the coefficient of discharge of a given Orificemeter. Apparatus are Orificemeter, U-tube manometer, collecting tank, stopwatch and a metal scale. The procedure to conduct an Orificemeter in a laboratory is, firstly you have to keep the main gate valve open and allow the water to flow through the Orificemeter. So initially you have to check the U-tube manometer, you have to remove the air bubbles and you have to check that both the limbs are same in a U-tube manometer. Then start the trials with varying discharges. So you can begin with a maximum discharge or with a low discharge and allow the flow to be stabilized. Then note down the manometer reading. Then by using the stopwatch, note down the time taken by the water in the collecting tank to rise to a known height, that is 0.1 meter rise or 10 centimeter rise. Then repeat the same procedure, vary the rate of flow gradually and note down the corresponding manometer readings and time t taken to fill the collecting tank for a 0.1 meter rise. So this is the observation and calculation. So initially you have to note down the inlet diameter of the pipe D1, then orifice diameter D2 in meters. With that you can calculate the inlet area A1 equals pi D1 square by 4 and orifice area, that is small a2 equals pi D2 square by 4. Area of the collecting tank can be calculated with B into L, that is the breadth of the collecting tank into length of the collecting tank. So with that you can calculate the theoretical discharge by using an expression, that is Q theoretical equals A1 into A2 into square root of 2G HV divided by A1 square minus A2 square. So here HV is the Venturimeter head, that is H into GM by GP minus 1. So here capital H will be equals to H1 plus H2. So here it has been shown as an H1 minus H2. So depending on the U-tube manometer connected in your experimental setup. So you have to note down the readings and you have to calculate the H. And GM is a specific gravity of mercury 13.6 and GP is a specific gravity of the liquid. So with that you can calculate the actual discharge, that is Q actual equals A into R by T. So once the Q theoretical and Q actual is calculated, you can calculate the coefficient of discharge CD equals Q actual by Q theoretical. So these are the observations and formulas you have to note down before conducting the experiment in the laboratory. Now let us perform an experimental conduction in the laboratory. Good morning all. So after discussing the theory concept of Orificemeter, now let us perform the experimental conduction in the laboratory. So this is the Orifice and Venturimeter, since both have been set up in the same equipment. So this is the starter. So this is a U-tube manometer. So since both the equipments are set up in a one frame, so we have to use the control valve and we have to open the Orificemeter valve. Venturimeter valve should be in a closed state. So this is the collecting tank. So this is the Orificemeter setup. So this is the inlet valve and this is the outlet valve. So you have to note down the dimensions of the collecting tank, and this is the sump tank. So YouTube manometer should be in a same level. So you have to check both the limbs should be in a same level. If not, by using valves, you have to remove the air bubbles and you have to make both the limbs at the same. After that, immediately you have to close the pressure valves. So since both the experimental setup have been framed in one, so initially while performing the orifice meter, the venturi meter pressure head valve should be closed and orifice meter pressure head valve should be opened. Start the motor so that the variations in the YouTube manometer readings can be noted down. So below the 0th level, you have to note down as a H1. This is the 0th level and this is the H1 reading. So you have to note down the H1. So again from the 0th line, you have to note down the above reading as a H2. So that you can calculate the H1 plus H2, you will get the variations in the head. Maximum discharge have been allowed. The water is flowing through the pipe. So you have to note down the time taken to collect water in a collecting tank. So first you have to close the butter valve. Then note down the reading. It is 0.1 meter rise or 10 centimeter rise. I'll start with a 12. So 12 to 22. So up to that, what is the time taken to collect water in a collecting tank? So that reading you have to note down. Then open the butter valve. Again the same procedure have to be followed and you have to perform for varying discharges. So firstly we have done for the maximum discharge. Now we will set for the medium flow. So similarly you have to note down the manometer reading, variations H1 and H2. With that you will get a total head. Then you can note down the amount of water that has been collected in a collecting tank. So time can be noted down. With that you can calculate the Q actual, and Q theoretical can be calculated by using a formula. With that you can calculate the coefficient of discharge. Noting down the readings in a laboratory, you have to calculate the Q theoretical and Q actual. So here the two trials have been shown. The first trial is for maximum discharge. So here we have noted down the readings, manometer readings, H1, that is a right limb reading. We have obtained 235 millimeter, and H2, it is a left limb reading. We have obtained as a 255. So with that you can calculate H equals H1 plus H2. So that is 490 into 10 power minus 3. Here the reading have been expressed in meters. So with that you can calculate the venturi meter head, that is HV equals H into GM by GP minus 1. So we have obtained 6.174. So once the HV is calculated, substitute all the values in Q theoretical expression and calculate the theoretical discharge. So for the first trial we have obtained 1.39 into 10 power minus 3. So for 0.1 meter rise, the time t have been noted down, that is 12.45. So with that you can calculate the Q actual, A into R by T. So Q actual we have got 1 into 10 power minus 3. So once the theoretical discharge and actual discharge is calculated, you can easily calculate the coefficient of discharge, 0.71, that is CD equals Q actual by Q theoretical. Similarly, you can vary the discharge and you can note down the readings. For the second trial, that is a medium flow, we have obtained 0.67. Similarly, you can carry out the third trial for low discharge, you will get the reading. So after carrying out the 3 trials, then you can calculate the average coefficient of the discharge, that is CD. So you will be getting in terms of 0.71 to 0.72. So you can note down here the coefficient of discharge which is obtained for orifice meter is little bit lesser comparing to the venturi meter.